Hello and welcome. In this module we will continue to discuss the optical transmitters. Particularly I would like to discuss a little bit more on the Zander modulator, and then we will see how we can use phase modulator that we discussed in the last module, as well as the Zander modulator that we have been discussing in the last module as well as in this module, how they can be used for modulating both analog signals as well as digital signals. That is to say, we can use them for analog modulation as well as for digital modulation. If you recall from the last module where we stopped discussion on the Zander modulator, we derived the input and output electric fields for this modulator. The structure of the modulator at its very simplest sense, we have not looked into the physics yet, would consist of the input waveguide through which we couple light from the source such as a laser, and then this light is split into two paths or two arms. Each of these arms are themselves phase modulator. So, you have one phase modulator at the top which is being driven by a voltage U1 of t, and there is a phase modulator at the bottom which is being driven by a voltage U2 of t, and then you get, once you combine these two phase modulator outputs, you will get the electric field at the output of the Zander modulator. If you now plot the transfer ratio of this, in the sense that if you take the electric field of the Zander modulator output and then divide that one by what you are feeding as the input electric field, and plot that one as a function of the difference voltage U differential. So, there is a D in the subscript here to indicate that this transfer function is actually a function of whatever the difference between the voltages U1 and U2 are. So, here we have defined UD as the difference between the two inputs U1 and U2. So, this difference voltage U1 minus U2 of t is the differential voltage, and we have seen that the electric field at the output is related to the input electric field, and that is getting multiplied by a factor which is cosine of pi u d of t by 2 v pi. So, this cosine which is getting multiplied is making this Zander modulator transfer function between the input and output electric fields into a nonlinear characteristic. This nonlinear characteristic is very evident over here, because this is not the characteristic of a linear system. So, this is the characteristic of a nonlinear system. So, this is a nonlinear relationship between E out and E in. If you now take the square of E out, or rather the absolute square of E out, what you get is the output power, which again is a function of time, because the output electric field could also be a function of time, because U d of t could be function of time. And if you take absolute square of the input electric field E in of t, you would get the power P in of t. So, now when you take the ratio of the output to the input power, in this case we will assume that the input power is held constant. So, whatever changes in the output power that you are seeing at the output of the Zander modulator is happening because of the time varying input voltage. So, as U d of t changes, so initially let us say U d of t is 0, at which point the output power is maximum. The reason why this would be maximum can be seen if you look at the structure here. See, the light power is coming in, okay, this is some constant power, this gets split into two equal parts. However, the fields are the ones which are really splitting, not the power. So, the fields split here, these two fields are still in phase with each other. Now, as the upper portion of the light passes through, so let me try and give you that graphical interpretation, hopefully it would be better to understand that. So, this power which is coming in or which is given here would this electric field which is input to the modulator gets split into two parts, both are in phase. Okay. In our simple model we will consider them to be in phase. Later we will see that on a waveguide construction there has to be a 90-degree phase shift between these two arms. Okay. However, that 90-degree phase shift is offset by another 90-degree phase shift at the coupler. Therefore, the overall phase shift will be 180. Then there has to be some additional delay that you have to put in one of the arms, so as to make the total phase shift without any application to be equal to 2 pi or 0 or its multiple 2 pi, 4 pi and so on. So, in this case, since the input electric field is split, we are modeling it as being split into equal parts, in the sense that the amplitudes of these two arms are equal and they are in phase, right. So, if they are in phase, while this is rising, this will also rise, while this is falling, this will also fall. So, essentially these two arms the electric fields and these two arms are in phase with each other. As they propagate, this fellow will undergo some phase shift. Okay. So, let us say if this is my reference electric field, then after phase modulation, let us say this is my phase shifted version. Okay. Of course, I am considering a time which is very small, so that I am able to denote it this by a phase shift. Actually, this phase shift will be a function of time, because u1 of t will be changing with time. A similar thing can be written down for in this case also, because ud of t is equal to 0. So, at this point ud of t is equal to 0, indicating that this u1 of t is exactly equal and is in phase with ut of t. Therefore, whatever the phase shift that the signal in the upper arm undergoes, the signal in the lower arm will also undergo the similar phase shift. So, at the output of the phase modulator as well, these two light waves in the two arms of the interferometer are in phase. Now, when you combine them, you essentially get the combined output which is in the full strength, right. So, because the phase shift of the two waves which are interfering happen to be 0, when the phase difference happens to be 0, then you get the maxima in the interference pattern. This is something that you know from your high school or first or second year college, where you might have done some experiments on Young's double slit interferometer. So, you know that whenever you have two waves which are interfering with 0 phase shift, you get maximum of the power, or the intensity will be maximum there, and that is the reason why you are getting a maximum in the transfer characteristic over here. And because I am looking at the normalization, the output power is divided by the input, the maximum power that you can get here is 1. This Zander modulator is not an amplifier, okay, it is just a modulator. It is an interferometer which is not an amplifier. Therefore, you not get any more power than what you are putting in. We do not have any gain elements inside this modulator. Now, by the same way, can we understand why the modulator transfer characteristic must go to 0 when the difference voltage becomes equal to V pi? We can understand that. Now, one way to understand this characteristic here is that we recall what ud of t was. Ud of t is u1 of t minus u2 of t. Now, if this has to be equal to V pi, we can have it in many ways, because all we are asking is the difference between the two signals must sum up to a constant. Now, I can have this in one case by having u1 of t equal to V pi and u2 of t is equal to 0. I can also have the same situation by having u1 of t is equal to 0 and u2 of t is equal to minus V pi, or I can split this V pi into half of each. So, I can have u1 of t equals pi by 2 and u2 of t is equal to minus V pi by 2. So, that the difference between these two voltages will again sum up to V pi. So, as you can see, there are an infinite number of choices, and we will simply assume this choice to discuss the modulator transfer function as why we are getting a 0, why is the modulator output going to 0 when the difference voltage becomes equal to V pi. To do that, we will go back again to this same characteristic. What happens here is that at the input side everything is alright. So, you have the light coming in, this light gets split into two parts, both are in phase at this time, which is perfectly fine. However, now look at what is happening. Because u2 of t is equal to 0, whatever the signal that you are getting at the output of the below phase modulator, that should be equal to the input of that phase modulator, because there is no phase shift. So, as long as the voltage u2 of t was different from 0, you would have obtained some phase shift between the output and input. Now, since that u2 of t is 0 here, whatever the output would be will be the same, that is, it would be in phase with the input signal and it will not have changed its phase, or you can say that the phase would be 2 pi, but in again nothing would actually change. Okay. So, you have the output of the bottom phase modulator to be exactly the same as the input. So, I am writing that by showing both these superimposed on that. Okay. So, both input and output are essentially the same signals. Okay. Let us keep this simple model in mind. Now, when you look at the top phase modulator, unfortunately that is not exactly same. Why? While the input is this one, what would be the output of the top phase modulator when u1 of t is V pi? To understand that, let us rewrite our, or let us recall the relationship of the phase modulator. So, I have E out of t is equal to E in of t, this is the phase modulator equation that I am writing. Okay. So, this is phase modulator multiplied by e to the power j pi u1 of t divided by v pi. This was the relationship between phase modulator. So, u1 of t was the electrical drive signal applied to the phase modulator, E in of t is the light source coming from the laser or the light wave coming from the laser, and this would be the output of the phase modulator. Now, you can very easily see that when u1 of t is equal to v pi, then I can replace this u1 of t by v pi, and now you can see very easily that the numerator should be v pi. So, this will cancel with each other, and what is exponential to the power j pi? This is nothing but cos pi plus j sin pi. Sin pi is 0, cos pi is minus 1. So, this is nothing but minus 1. So, what you now have is that the output electric field is negative of the input electric field. There is no problem here. Sometimes I get a question as to how can the electric field be negative with respect to the output. I mean, output electric field could be negative with respect to the input. Would it mean that power also is less than 0? Which is wrong, because the power associated with this output electric field is obtained by taking the magnitude square of the electric field, and because this minus sign would not really matter when you take the magnitude of the electric field, the output power would be exactly equal to this input power. So, there is no problem in power relationship. Electric fields can be negative, but power would always be a positive quantity. Okay. So, this is something very important to keep in mind. Many times we see that, oh, power can be negative. I mean, some students have this thing that power can also go negative, in these situations, but it cannot happen that way. Power is not negative, power is always positive because of this magnitude square thing. Alright, having discussed or digressed a little bit, let us get back to the track. So, what we have observed is that when u1 of t is equal to v pi, then the output electric field is minus input electric field, which means that if this is the reference voltage that you have given to the input of the phase modulator, the output of the phase modulator would be an exact opposite of that, right. It would be 180 degree out of phase with the input. Now, you look at the two red waveforms, one at the top and one at the bottom. These two are now 180 degree out of phase. Now, you go back and think about the Young's double slit experiment, that if I have two waves which are out of phase by 180 degrees, that is, if they are out of phase, then what would be the output on that you would see on the screen? It would be a 0, because two waves which are in same in everywhere else except their phase is 180 degree out of phase with respect to each other will interfere, will destructively interfere to give you a 0, right. So, when you take this sine wave and add to that a sine wave which is 180 degree out of phase with the sine wave, all you get is a 0 here. So, what you get at the output is 0, and that is precisely what we have shown over here, saying that the output electric field must be 0 at this particular characteristic. So, it is hopefully understood that when the difference voltage ud of t is going through 0, then there is constructive interference here, and when ud of t is going through v pi, there is destructive interference and the modulator produces nothing, or the output of the modulator is 0. So, in between these two extremes is the cosine characteristic. Okay. As I said, when you look at the power characteristic, the characteristic of the power always being positive will mean that while the field is going negative, the power is actually going positive. And for this lossless modulator that we have assumed, this would be a periodic function. Okay. So, this would be a periodic function. The power is periodic with a period of 2 v pi, because this is over one period for the power, whereas the electric field would be periodic over the same this one, but this would be this 2 v pi. Okay. So, we have now discussed two modulators, one is the phase modulator and the other is the Zander modulator. Let us try to put them into use to see how we can modulate the phase of the light signal and to realize the phase modulation or amplitude modulation. Since it is amplitude modulation that we are normally familiar with, let us actually begin with a slightly complicated example of modulation, that is Mach-Zander modulation. Okay. Recall that for a simple amplitude modulator, all you require in the functional terms is that I have the message signal m of t and I have the carrier signal c of t, which would produce a signal s of t, which is some m of t into c of t. This c of t of course will be a sinusoidal carrier as we discussed in the last module, and m of t would be a message signal or the baseband signal. So, this is the baseband signal. We are assuming that at this moment m of t represents an analog waveform, and this type of a modulator is called as a double sideband suppressed carrier modulator. Okay. There are in fact other ways of amplitude modulation. One which is actually the original amplitude modulation will have some bias value. So, it will have some 1 plus KAM m of t, where KAM is some constant. This whole thing is getting multiplied by C of t. So, if you look at the spectrum of this for sinusoidal modulation, you will find not only the carrier term, but you will also find the upper and lower sideband. So, the carrier is also transmitted here, whereas for the double sideband suppressed carrier system, you do not have any carrier in the center. Okay. So, however, both are amplitude modulators themselves. Okay. Now, how can we realize this functional relationship with the Mach-Zander modulator? Let us look at what the Mach-Zander modulator functional relationship is by putting a symbol for the Mach-Zander modulator. Okay. So, this is my Mach-Zander modulator, to which I am supplying light. So, let us call this as C of t, and I should of course also supply m of t, but I know that this relationship is not exactly this multiplication, right. I know that the output of the Mach-Zander modulator, if you take this C of t and remember that this is nothing but the electric field at the input, and this m of t as the difference signal ud of t, right, in our terms for the MZM, the output of this one will be called E out of t is actually given by E in of t into cos of pi ud of t divided by V pi, or sorry, there is a 2 V pi here. So, this is the characteristic that we have, right, and well, instead of E out of t, let us write this as S of t. So, what you see here is that S of t is actually given by C of t. This is for the Mach-Zander modulator. I am actually trying to compare the conventional amplitude modulator discussion that we find in communication systems to the Mach-Zander modulator functional relationship that we have just derived, okay, or that we have been discussing. This Mach-Zander modulator, if you were to map m of t to ud of t and C of t sinusoidal carrier to the light input electric field E in of t, and map S of t to E out of t, this is the relationship that you get, C of t into cos of some constant that we do not have to worry, we can call that constant as KAM times ud of t. Clearly, this is not exactly the same as this relationship m of t into C of t, because of the presence of this cosine term here, right. So, this is not going to give you an exact double sideband suppressed carrier. Is there a way out? Is there a way in which we can approximate this nonlinear characteristic with that of this characteristic that we have? Okay. Is there a way in which I can kind of eliminate cos by placing some restrictions on ud of t and KAM? If I can pick this KAM and impose certain criteria on ud of t, is there a way for me to make this one almost equal to this particular characteristic? Let us see how we can do that. Well, we remember what this KAM is, because KAM is nothing but pi by 2 V pi in this particular mapping that we have done, and ud of t, this is the other thing that we can play around. We cannot of course play around with C of t, you require the carrier for modulation to happen. Let us suppose that I can write ud of t as consisting of some DC component plus some AC component. Okay. So, the DC component will be constant and the AC component will be another, it is a small signal component. Okay. AC component is very small, the magnitude of AC component or the peak value of the AC signal is very small compared to the value UDC. Okay, so let us also put down in terms of the magnitude itself. So, this has to be very small compared to UDC. Okay. Now, if I take UDC to be equal to V pi, okay, so if I substitute this V pi condition into this expression for the output electric field, I get E out of t of the Mach-Zehnder modulator is equal to E in of t times cos pi by 2 V pi UDC, which is V pi, plus UAC of t. If you expand what is there in the bracket inside, what you see is E in of t times cos of V pi will cancel from numerator and denominator. What I get is cos pi by 2 plus pi by 2 V pi UAC of t. So, UAC of t is a very small component compared to UDC. At the same time, while that is getting multiplied by pi by 2 V pi, if I take the peak value of AC of t and denote it as UAC, this peak value multiplied by pi by 2 V pi will be the peak value of this voltage, correct? That would be the peak value of this voltage. If we choose this to be very small compared to 1, that is, if we choose this component to be a very small quantity compared to pi by 2. Okay. So, that is the idea. So, we choose this one to be a very small quantity compared to pi by 2. Okay. Now, let us expand this term in the bracket, or let us expand this cosine term by recalling the trigonometric identity that cos of A plus B is equal to cos A cos B minus sin A sin B. Okay. So, if I apply this trigonometric formula, what I get for the output electric field is E out of t is equal to E in of t times cos pi by 2 cos of, let us call this pi by 2 V pi, and whatever the AC peak value as sum K A. So, I have cos K A UAC of t minus sin pi by 2, this E in of t is a common factor for everything, sin pi by 2 into sin of K A UAC of t. Now, I know that cos pi by 2 is 0. So, this entire term will be equal to 0. I know that sin pi by 2 is equal to 1. So, what I get for the output electric field is minus E in of t, and we are assuming that K A into UAC of t is a small number, right. It is for a small number, sin theta is approximately theta itself. So, I can eliminate this sin from this expression and I write K A into UAC of t. Okay. The output is very small because we are actually operating at the 0 point of the Mach-Zehnder modulator. The output would be very small as you go around here. What you would like would be to try and move the operating point somewhere else, so that I can still see a linear relationship, that we will check later. But at this point, since we have chosen this to be equal to V pi, as the input voltage swings back and forth, right, as the input voltage changes over here, the corresponding output change will happen over this transfer characteristic, and this output is small because we are operating near the 0 point of the Mach-Zehnder modulator. But what we have managed is to obtain this relationship. We have obtained minus K A, which is some constant, does not matter, but more importantly, if you look at the remaining part of the expression, you have E in of t, which was equivalent of C of t for us, and UAC of t, which was equivalent of M of t. So, as long as your Mach-Zehnder modulator is biased at V pi and you are applying a AC signal, AC drive voltage, which is very small compared to the DC voltage that you have applied, you can approximate the relationship of E out and E in by C of t into M of t type of a relationship. So, that cosine nonlinear characteristic has been removed, but at the expense that the output power has drastically reduced, because what is the output power? The output power is magnitude square of this term, right, and in this magnitude square you will see that there is a magnitude of K A square involved. As K A itself is quite small, K A square is even smaller than K A. So, the output power is very small, but the good news is that you have been able to obtain amplitude modulation. So, if your m of t or equivalently if your uac of t happens to be an analog signal, what you have obtained is an analog modulation. Okay. This is one way of operating the Mach Zander modulator in order to perform amplitude modulation or amplitude modulation of an analog signal.